Welcome to the fifth video on polar graphing in a series of 8, roses. Here's our first equation that's going to produce a so-called rose graph. And these have sort of a flowery appearance, so you'll see later why they chose that name. As usual, polar graphing is all about analyzing how changes in theta affect r. And this is the typical four-quadrant analysis that we've been doing if you've been watching videos 3 and 4 in particular. But something is changed here, and for the first time in this video series, the argument of our trigonometric function is no longer just theta, it's now a multiple of theta. And that, as we'll see here in this first problem, changes our analysis. Here's the logic. We want to know what the argument of the trig function being in different quadrants has an effect on r. We're less interested in theta being in the particular quadrants as we are analyzing what happens when 2 theta runs through each quadrant. For example, analyzing as 2 theta ranges from 0 to pi over 2 is the same as analyzing theta values from 0 to pi over 4. Restated, if theta goes from 0 to pi over 4, 2 theta will go from 0 to pi over 2. Likewise, when 2 theta is in the second quadrant, represented this way, theta itself would be between half of those values. And if you're getting a little lost in all the fractions of pi radians, let's look at it this way. We really want to think about what theta would have to be for 2 theta to be in quadrant 1. And let me say these in degrees just for simplicity. If theta is anything between 0 and 45, 2 theta will be between 0 and 90. Similarly, if theta is between 45 and 90, 2 theta will be between twice those values, or 90 to 180. If theta is between 90 and 135 degrees, 2 theta will be between 180 and 270, or be in quadrant 3. Essentially, what you want to do in these problems, instead of looking at in theta in 90 degree or pi over 2 increments like we have been in this video series, we want to look at theta in half that size increments because of our 2 theta. In fact, that may not be enough though, because that only brings us up to a theta value of pi. So I've decided to extend this table twice as long as we normally would, looking at 45 degree increments of theta all the way through. And at the end of the day, we're less interested in 2 theta than just analyzing how theta has an impact on r. If you followed a lot of that logic, that's great. That's not the typical way people think. So let me rephrase it this way. If we have a 2 theta, then we want to break each quadrant into 2 parts and analyze them in halves. In other words, anytime you see a 2 theta, let theta go in 45 degree increments, and you'll have an easier time analyzing the function. Move that over there. Okay. Well, to do this, I'm going to have to plug in all of these values into the original function. Of course, I'm not showing the trigonometric algebra, but if you work each one of these out, which you can do, you'll get these answers. And now, what I can do is say to myself, okay, as theta goes from 0 to 45, r goes from 0 to 3. And that tells me what's happening to r in the first half of the first quadrant. Then, as theta goes from 45 to 90, r shrinks from 3 back to 0, and that tells me what's happening in the second half of Quadrant 1. Then, as theta goes from 90 to 135, r shrinks from 0 to -3, and that tells me what's going on in the first half of Quadrant 2, and so on and so on and so on. And of course the question is, how do these changes in r affect the graph? First, let's watch what happens as theta sweeps from 0 to pi over 4. In other words, through the first half of the first quadrant. You'll notice our table indicates that r is going to go from 0 to 3. So here's theta going from 0 to 3 as we sweep through the first half of the first quadrant. You'll notice in the second line of our table, theta is going to go back from, r is going to go back from 3 to 0 as we complete Quadrant 1. So here's r going from 3 back to 0, and now Quadrant 1 is complete. Now let's go through Quadrant 2. You'll notice the third line in the table has r going from 0 to -3. That means as theta sweeps through the first half of Quadrant 2, r will be negative, meaning behind theta in Quadrant 4. So here's r going from 0 to 3, -3, excuse me. And as we complete Quadrant 2, you'll notice the table in the fourth line indicates that r is going to go from -3 back to 0, which it's doing here. Now the fifth line in the table is where Quadrant 3 begins, and that shows r going from 0 to +3. So here's r going from 0 to +3. And as the next line indicates, r is to go from 3 back to 0 as we finish this quadrant. And finally in Quadrant 4, you'll notice in the next to last line on the table that r is going to go from 0 to -3 and -3 back to 0, meaning that it'll be negative the whole time, or behind Quadrant 4 in Quadrant 2. So here's r going from 0 to -3 and from -3 back to 0. Here's another Rhodes equation. Of course, we want to ask ourselves, as usual, how does theta impact r? But this time we have a 3 theta. The larger that coefficient of theta is, the more work we tend to have to do. Now, this isn't going to be a long enough table, but the logic here is this. If I have a 3 theta, or as the argument of my trig function, I'm going to want to break the first quadrant up into 3 parts, 0 to 30, 30 to 60, and 60 to 90. So I'll need a much longer table to handle this, and what I'm going to want to do here is analyze theta in 30-degree increments because of my 3 theta. Because every time theta changes by 30 degrees, 3 theta changes by 90, and that will give me the quadrant by quadrant analysis. So I've got a lot to plug in here. Because of the clutter of the screen here, I did not show the work, but these numbers that just appeared represent me plugging all these theta values into the equation and finding my r values. Okay, so as theta goes from 0 to 30, r goes from -4 to 0. I'll represent that here. As theta goes from 30 to 60, r goes from 0 to 4. And as theta goes from 60 to 90, r goes from 4 back down to 0. And you could continue doing the same logic, but you don't need to see all those analyses. This is what we end up with. And as usual, our question is, what's the graph going to look like based on all these changes in r? Notice in our 12-line table, I've broken the values up into 4 quadrants for simplicity. Let's start with quadrant 1, and we're going to let theta go from 0 to pi over 3. We're going to go through the first 1/3 of quadrant 1. Well, notice that on the top line of the table, it indicates that r is going to go from -4 to 0, meaning it's going to be behind theta. Here's r going from -4 to 0 as we go through the first 1/3 of quadrant 1. In other words, letting theta go from 0 to pi over 6. Now let's let theta go from pi over 6 to pi over 3, in other words from 30 to 60 degrees. Notice here that r is positive, going from 0 to +4. Here's r going from 0 to +4 as we go through the next 1/3 of the first quadrant. And for the final 1/3 of the first quadrant, r is going to go from 4 back to 0. Here's r shrinking from +4 back to 0, completing quadrant 1. Now, let's start quadrant 2. In the first 1/3 of quadrant 2, excuse me, r is going from 0 to -4, meaning it'll be behind theta in the 4th quadrant. Here's r going from 0 to -4 in the first 1/3 of that quadrant. Then notice r is to go from -4 to 0 in the second 1/3 of that quadrant. And finally, if you notice the last line in quadrant 2, r is to go from 0 to +4. Here's r going from 0 to +4. Now, we're only 2 quadrants through, but this problem, for whatever reason, just turns out to be one of those problems where going from 0 to pi, or just letting theta sweep through the first 2 quadrants, is enough to get the entire graph. But you wouldn't know that necessarily. So let's go through quadrant 3 and 4 as if we didn't know that. But notice in quadrant 3, if you look at the table, lines 7, 8, and 9, you'll notice that r goes from 4 to 0, 0 to -4, and -4 back to 0. And you can see all that playing out here. Watch the graph. Here's r going from 4 to 0, then from 0 to -4, meaning it's behind theta, and then from -4 back to 0, and you'll notice that we're just getting duplicates of points we already knew were on the graph. And finally, as we sweep through quadrant 4, we get more duplication, thus completing the graph of this rows. I'd like to share some generalizations with you that I've noticed over many, many years and much experience doing these. Roses have the equation some number times cosine of a multiple of theta, or some number times a multiple of sine of a multiple of theta. In other words, what you see at the top of the screen. And one observation that I've made, and it's actually provable if one had the math skills to do so, it turns out if n is odd, then the rose has n petals. And by that I mean, if we have a 3 theta, we're going to have 3 petals in our rose. However, if n is even, we're going to have 2n petals, meaning twice the value of n. For example, when we had a 2 theta, we had 4 petals. These two examples you're looking at are the ones we saw. Here's one we didn't see in the video. If I have a 4 theta, I'm going to have 8 petals in my rose. But if I have a 5 theta, 5 being odd, I'll only have 5 petals in my rose. And that's the generalization of the number of petals of the rose that you can expect. Now, which way are they oriented? Well, the sines and cosines and positives and negative coefficients in front of them will rotate them around. There's too many generalizations I could make about that, so I won't. But that's the general idea of what you can expect when you're graphing a rose. And that completes the 5th of 8 lessons.